it's our honor to hear Muhammad's presentation today. He will give us a very interesting topic about highly stretchable and printable silver nanowire inks for flexible electronics. And after the presentation, and every audience can ask their questions or give some comments about your presentation. So if you are ready, you can start your presentation now.
Thank you, Zu. Thank you for introducing me and my topic. I think I'm ready for presenting. So, welcome everyone. My name is Mohammed Kaya Harman, and I am working on highly stretchable and printable silver nanowire inks for flexible electronics under the supervision of Professor Irene Goldthorpe. This here, you can see the outline for my presentation. My presentation have an introduction section which will cover printed electronics and flexible and stretchable electronics and the printing technologies, printable conductive inks, ink formulation, state-of-the-art conductive silver inks. And after the introduction, it will be problem statement, stretchability and enhancement strategies for silver nanowire inks, commercial stretchable inks versus silver nanowire inks, and summary and future work. So conventional and printed electronics. Let's, as you all know, one of the main methods for conventional fabrication is photolithography. And photolithography is very complicated. It's really expensive, and it's a subtractive manufacturing method. And as you can see on the right-hand side, you can see this figure is showing a regular photolithography for device fabrication. For photolithography, you need a deposition, you need the photoresist, you need to expose it, you need to develop it, you need to etch it, and then you need to remove the PR to have your final patterned film for your devices. As you can see, this is a very, there are lots of steps. It's very complicated. You need really expensive equipments. And this is just for one layer. If you need like 5 or 10 layers for a device, it's getting much, much more complex. But for printed electronics, you can see printed electronics is fabricating devices by using the regular printing technologies. You can see one of the main advantages of printed electronics is device film deposition and patterning can be done simultaneously. And you can see there is not much steps. It's really simple. It's a really low cost. And another advantage is you can fabricate on a really large scale. And it's an additive manufacturing. It's not, that's why it's clean. And also another advantage is since there is not complex steps like this, and it's also low temperature, you can also print on flexible and stretchable substrates as well. And let's talk about flexible and stretchable electronics first. So flexible, every device that has fabricated on a flexible substrate or that can tolerate bending or strain is known as flexible electronics. There are different kinds of methods for fabricating flexible and stretchable electronics, but printed electronics is the main, one of the best methods for flexible and stretchable electronics because they are low cost, they are simple, they are low temperature. Because you can see the substrate that we use for flexible and stretchable electronics are like PET, TPU, PDMS, and textile. They can't tolerate high temperature. And there are some of different degrees of flexibility. These are bendable, conformal, and stretchable. Bendable electronics are like, you can see, they can only bend. And conformal electronics, they are also flexible, but they are permanently shaped. You cannot change their shapes. And stretchable electronics, they can tolerate strain. The substrate and the devices can tolerate a tensile strain. So stretchable electronics, why stretchable electronics is so important right now? And because with the Internet of Things, in a couple of years, next generation wearable devices needs to be comfortable. They need to be low cost. They need to be low weight. So that's why right now a lot of people are working on stretchable electronics. And stretchable electronics has a huge application area. We can see only a small number of application areas, such as electronic skin, sensors, energy harvesting, health monitoring, touch panels, transistor arrays, energy storage, and electronic display. And some of the challenges with the current stretchable electronics, there is a trade-off between conductivity and stretchability. So that's why highly stretchable conductors have low conductivity. High conductivity conductors have low stretchability, and they are currently high cost and complicated. But these complicated and high reduced with using printed electronics. Some of the printing technologies are inkjet printing, gravure printing, aerosol jet printing, and flexographic printing. Each of these printing methods have different ink requirements, different viscosity range, different throughput, different requirements, and different resolution. So depending on your application and your needs, you can choose one of these printing technologies for printed electronics. And since we are using screen printing, I will focus on screen printing more, and I will explain screen printing. So screen printing is one of the most popular printing technology in industry. More than 95% of the industrially printed electronics fabricated by screen printed. It's very simple. It's really low cost. You can see the schematic that shows screen printing. For screen printing, you just need a screen or frame. You need a squeegee to sweep the ink. You need an ink, and then you need a mesh. Here you can see from the side view, when the squeegee sweeps the ink, with the pressure, these inks can be dropped from the mesh, and then you can. This is your substrate, and you can print your ink with just sweeping the squeegee. You can see a picture of screen printing as well. It's some of the advantages of screen printing is you can print high viscosity inks, and micro-sized fillers can be printed, because here these meshes are like really large, and you can print micro-sized fillers. Usually you cannot print micro-sized filler with inkjet printing because that causes clogging issues. And another advantage is high aspect ratio films can be printed. You can print really thick films, like larger than 10 micron. You can print on a really large area. It has a low resolution, around 30 micron, but depending on the application, it's not an issue, and can be printed on curved substrates with screen printing. Printed electronics, you are using printing technologies. Only difference with regular printing that you are doing at home is the using of functional inks. And these functional inks can be for the electronics. It can be conductive, non-conductive, or semi-conductive. And as you all know, for all devices, conductive parts are the crucial. So that's why conductive inks are also crucial for printable electronics. They can be used as interconnects. They can be used as device electrodes and antenna and etc. And these conductive inks has expected to reach 4.4 billion market size by 2024. Here are some of the areas that printed conductive inks that use, like RFID tags, solar cells, switch, e-textiles, displays, and TFT arrays. And some of the materials that can be used are metallic, like it can be silver, copper, or gold. But since silver has the highest conductivity and has really good air stability and lower cost than gold, so silver is the main for metallic. There are polymer and carbon-based as well, but their conductivity is really low, and they are mechanical. Even though they have really good mechanical properties, their conductivity and performance is really low. And the current challenge with conductive inks is the long-term stability. So for an ink formulation, there are 4 main ingredients. These are fillers, solvents, binders, and additives. Fillers are the conductive components, which makes the ink conductive. Solvents, you need solvents to have an ink to have a liquid form. Usually alcohol or other solvents can be used as solvents. And binders, they keep the ingredients together. And additives, they are for adjusting the ink properties, like there are thickening agents for adjusting viscosity, or there are deformers to prevent foam generation, and there are leveling agents to provide a good leveling for the ink. And filler concentration, filler concentration of the ink depends on the percolation threshold. Percolation threshold is at percolation threshold is the concentration that matrix changes its characteristic drastically. So for conductive inks, we can consider this characteristic change from non-conductive to conductive. Let's take a look at this plot. Here you can see the electrical resistivity, and it's a function of filler concentration for carbon black. And you can see initially at low concentrations, so this also showing the carbon black particles for different concentrations. Like here, since you can see the concentration is really low, they are not in contact, there is not a conductive network between the particles. That's why resistivity is too high. And when you keep increasing the filler concentration, concentration slowly, you can see at some point there is a sudden change from resistivity from being non-conductive to conductive. So this is known as percolation threshold. So this percolation threshold, you need to know the percolation threshold for ink formulation to have a conductive ink. That depends on the geometry and size and aspect ratio of the materials. And another aspect is viscosity. So depending on the printing technology, you need to adjust the viscosity of the ink as well. So state-of-the-art silver inks have either silver nanoparticle or silver flake. Silver nanoparticle, as you can see, they have like a circular particles in nanometer scale, usually lower than 100 nanometer. And since they have, since they are really small, they have really low sintering temperature because they have really high surface energy. But also, since they have a really high surface energy, they have really low dispersion stability. So that's why you need to also use capping agents for them. And there is a small contact area. You can see that between each nanoparticles, there is like very small contact area known as dot-to-dot contact, and they are not stretchable enough. And another state-of-the-art silver inks use silver flakes, and most of the commercial inks also use silver flakes because they are really low cost, they are really simple. They have, you can see they have much larger contact area. Flakes are in the micron scale. First of all, I should say that they are much larger than nanoparticles. That's why they have high sinteric temperature. They are much larger particles, up to 10 micron, and they have that's why they have a high packing density. They have a large contact area, which is better surface to surface contact, much better resistance, and these are not stretchable as well. There is another option, silver nanowires. These are cylindrical shaped with 30 to 100 nanometer diameter and up to 150 micron length. You can see the silver nanowire here, and you can see a closer look here. These are like cylindrical long particles. And these nanowires can be synthesized by a very simple solution process. They have since they have a really high aspect ratio, they have much lower percolation threshold. With comparison to other nanoparticle and flake inks, usually nanoparticle or silver flake inks, you need to have at least 70% of silver to have a conductive network. But with using silver nanowires, you can have like 1% of silver nanowire might be enough to have a conductive network. Since they have really high aspect ratio, you can have much lower percolation threshold. They have much lower sinteric temperature, and they have higher conductivity at a given fill fraction. And one of the main advantages of silver nanowire inks is, as you can see here, they can tolerate really high numbers of strain. And this is really advantageous for stretchable electronics. Problem statement: state-of-the-art and commercial silver inks are not stretchable enough. Even though silver nanowires have been studied by different groups, only a limited number of people have investigated the stretchability of silver nanowire inks. And no one investigated the methods to increase the stretchability of silver nanowire inks before. So here, that's why we will study the stretchability enhancement strategies for silver nanowire inks. Methodology, here we can see the ink formulation. We have used a silver nanowire solution and a PVP solution, and by mixing them, we can get our silver nanowire ink. We screen printed our silver nanowire ink on a TPU substrate with a 48 mesh screen, and then we sintered at 65 degrees for 30 minutes. For the characterization, for the characterization of stretchability, we used a linear stage, tensile strain cycling with a linear stage, 250 cycles of 20% tensile strain, and electrical resistance measured with a digital multimeter simultaneously during the tensile straining, and sheet resistance was measured by a 4-point probe, and printed ink morphology was characterized with a scanning electron microscopy. Effect of length and diameter. Initially, we investigated the effect of length and diameter of the nanowire ink. And here, this plot shows the effect of increasing length. This plot shows the effect of reducing diameter. In order to study effect of length, we used, these are showing a commercial silver nanowires, A30SL, A30, and A30UL. So you can see the average, the diameter and nominal length for the nanowires. These all three have the same diameter and different lengths as 5, 30, and 150 microns. And for the diameter, we use A30UL, A70UL, and A100UL. You can see they have different diameters as 30, 70, and 100. And this table shows the initial resistance for all of them. Let's take a look at the effect of length first. You can see when we increase the length, this magenta plot is showing the 150 micron, and it has the high, this plot is showing the resistance change, and for this is showing the stretching cycles, 250 cycles, and you can see for stretchable electronics, minimum resistance change is better. So a minimum resistance change is expected for stretchable electronics. We can see that here we have the minimum resistance change with the longest nanowires, 150 micron, and you can see the longest nanowire have the highest, the lowest initial resistance as well. And if we take a look at the different diameter here, the same plot, and you can see 100 nanometer, 70 nanometer, and 30 nanometer, and stretchability increases with reducing the diameter as well. And also stretchability from the different diameters, 30 nanometer one have the lowest the lowest initial resistance, so that which means that stretchability and conductivity increases with reducing the diameter and increasing the length of the nanowire inks. Here, and then we studied the effect of concentration. For that, we tried different concentrations of ink for 5% silver nanowire, 10%, and 15%. Here you can see 5% ink has the minimum resistance change. And that means that lower filler concentrations lead to more stretchable inks. So one of the main reasons for that, when you increase the concentration of nanowires, it's from some point it starts to at higher concentrations, it starts to behave like bulk-like properties. So that's why when you increase the filler content, you are reducing the stretchability. And effect of sintering temperature. For this, we tried 3 different sintering temperatures, 25 degrees, 65, and 100. And you can see the initial resistance of them. Even though 100 sample centered at 100 Celsius has slightly better than 65 degrees initial resistance, the sample centered at 65 degrees had the best stretchability. You can see the magenta is 65. So usually people were always sintering their silver nanowire inks at really high temperature to get good conductivity. They were focusing on the conductivity, and then they were saying like for high conductivity, we need the highest temperature that substrate can tolerate. But here we see that lower temperature sintering can have much better stretchable silver nanowire inks. And here you can see the SEM images for 65 degrees and 100 degrees as well. 65 degrees has much better nanowires and much smoother nanowires, you can see. And another study that we did was the effect of welding method. In order to do that, we compared thermal sintered, plasma sintered, and calendared silver nanowire inks. we used the thermal, compared the thermal ones with, we also plasma sintered our silver nanowire inks with oxygen plasma, and we calendared with a hot rolling machine, but at room temperature. You can see a plasma sintering is making the nanowires nanoporous, and calendaring is making a more planar surface of nanowires. All of the nanowires are stick to the surface after rolling twice, and they have much planar network. And here you can see the heat sintered with comparison pressed and plasma sintered. You can see plasma sintered one has the lowest initial resistance and also highest stretchability, which the magenta curve shows the plasma sintered here. And another thing is silver nanowire inks. Usually silver inks have an issue of oxidation. So this oxidation increases the resistance with time, and also it reduces the stretchability as well. So here you can see so this orange plot shows the bare unpassivated uncoated silver nanowire ink, and you can see at 60 days resistance changes 4.5 times. And for this we found a very simple solution. We are coating Mayrod coating a liquid polyurethane on top of silver nanowire inks and UV sintering for 15 seconds. And with this industrially applicable, very simple method, you can see that resistance change can be reduced. And also you can see this orange plot is showing a bare silver nanowire ink, and the blue curve is showing the passivated and polyurethane coated one. This, you can see stretchability is also increased when we encapsulate silver nanowire inks with a stretchable polyurethane. And another interesting thing we did was comparing the commercial stretchable inks with silver nanowire inks. You can see we used two of the most widely preferred commercially available highly stretchable inks. These are the SEM images for those commercial inks. And you can see that they are silver flakes. And here you can see that the comparison of commercial ink 1 and commercial ink 2 with nanowire ink, plasma sintered nanowire ink. You can see commercial ink 1 increases after 250 cycles, increases around 500 times resistance change, and commercial ink 2 is having 100 times, while our nanowire ink is only having 1.3 times resistance change, which is a really good result for stretchable electronics. And we also compared increasing the strain with like 5% increments up to 150%, and we observed the resistance change since the commercial 2 provide better. We used commercial 2 here. You can see at 110%, commercial ink 2 has resistance change much more than 10,000 times and lost conductivity, while our silver nanowire ink can tolerate 100 up to 150% cycle with only 16 times resistance change. It's a really low resistance change at this high strain value. And for the summary, this table shows the state-of-the-art silver nanowire inks, their Philip concentrations, their aspect ratios, their sintering temperature, resistivity, and maximum strain. This 3 and 4 shows the stretchable silver nanowire inks. The others are regular silver nanowire inks. And you can see the aspect ratio of silver nanowires. We printed the highest aspect ratio, 2026-66 aspect ratio, the highest usually they are in 500 or 200 in the range. So this is the highest aspect ratio in the literature. And you can see they have a sintering temperature usually around 120 to 150. We have much lower sintering temperature at 65 degrees. We have a really good resistivity, really low resistivity, and more importantly, our ink can tolerate, while other state-of-the-art silver nanowire inks can tolerate 70 and 80% maximum strain, our ink can tolerate 150%. So this plot shows this maximum strain and conductivity at maximum strain for state-of-the-art silver nanowire inks, and also for silver flake, for polyaniline, for gold nanoparticle, and this comparing this work. So usually almost all of the stretchable inks, they are in this gray shaded area. So this gray shaded area means if if an ink, stretchable ink has really high conductivity, it can tolerate really low maximum strain, or if they can tolerate really high strain, they have really low conductivity. So they are usually stuck in this region, but we can see that our work, silver nanowire ink with optimization, there is a breakthrough in both of these for both conductivity and maximum strain, and then we are having a really high, we can tolerate a really high maximum strain with a really high conductivity. And for the future work, we are planning to combine different nanostructures of different materials and shapes for hybrid silver nanowire ink to reduce the cost of the silver nanowires. And using these silver nanowire inks for different applications, such as a fully printed stretchable graphene oxide field effect transistor. You can see the device structure here, and you can see the device fabrication steps here. We are planning to do a bottom gate top contact field effect transistor. We are planning to print the gate electrode first, and then printing the dielectric ink, and then depositing, spin coating the graphene oxide, and then printing the source and drain. So this we are preparing. We are planning to fabricate a highly stretchable and high performance field effect transistor. Here is my references. Thank you for listening to me. I can have your questions if you have.
Thanks for the presentation. Is there any comments or questions from the audience?
Yeah, if no one else has questions, I have a couple questions. I'll put my video on so you know who's talking. Well, thanks, Mohammed. It was very clear. You're a good speaker. I enjoyed the presentation, so thank you. I had a couple questions about some of the advantages of screen printing. And maybe I didn't quite catch this, but what do you mean by high aspect ratio printing? Does that mean that you can print like thick lines?
Yes, I'm just coming to that presentation really quick. Just a second. Okay, yes, high aspect ratio films means like usually with other printing technologies, with inkjet printing, aerosol jet printing, and flexographic and gravure printing, you cannot print really thick films. Their advantage is also printing thin films. Like inkjet printing, they can print like in nanometer scale films as well. But for printing like really thick films, because some of the devices, really thick films are needed like 1 micron or 5 micron. So this is like really time consuming to print with inkjet or other methods. So that's why this can be a really good advantage for industrial applications. You can print even larger than 10 micron with a really, because this is just for inkjet printing, you need to print like multiple times, like at least 5 times to have a thick film. But with screen printing, it's very simple. With just one sweep of the ink, you will have 10 micron ink. So that's the advantage.
Yeah, that is, I mean, that is good, because the thicker, I mean, the higher, or I don't, it's confusing to me talking about thickness, width, and height. But yeah, the higher the height, the more conductive the lines are going to be. So yeah, that is good. The other question on the screen printing is that, so the viscosity of the ink, it has to be more viscous for screen printing compared to some other printing technologies.
Yes. It needs to be sometimes it's even called paste because it's really viscous. For other printing technologies, they have a really short range, and they usually have really low viscosity inks. They are even in solution form, but for screen printing ink, that's really viscous, and that's needed as well, because as you can see, this ink is, while staying here on the gap on the mesh, it's not being dropped to the substrate, so it's just staying there. So that ink has like a rheological non-Newtonian properties. So when you apply force to that high viscous ink, that viscosity of the ink is being reduced. So with reduced ink viscosity, so that ink flows from these openings and being deposited on the substrate. So otherwise it can stay here without sweeping the squeegee. That's why high viscosity inks are required for screen printing.
And are there advantages of that? Does that mean that you can use higher filler concentrations?
Yes, that's a really important advantage as well. Like usually, like these micro-sized fillers, they are really high viscous as well, highly viscous, and you cannot print them easily with other printing technologies.
Yeah, okay,
Not
cool.
other than the size. So yes.
All right, thank you.
Thank you.
All right, if no one else has questions, I have one more question. So it seems like the thermal tolerance of your TPU substrates is around 100. What about other common stretchable substrates like PDMS? Do you know what, can they tolerate higher temperatures?
I don't have any idea about the thermal budget of the PDMS substrate.
Okay. Yeah, I think I would guess in general stretchable substrates are pretty thermally sensitive.
Yes.
But yeah, it just because it'd be good to see what happens to your ink if you anneal it at even higher temperatures, like the typical temperatures that other people use,
yes.
And see what happens. Okay, thanks.
Thank you.
I did have a question too, if it's okay.
Yep, go ahead.
When you were talking about the curing temperatures, you showed the SCM images, and there was some sort of crystals on the nanowires cured at 100 degrees C. Do you know what those were?
Just okay, this slide. So here, so we have a couple of ideas about them. So they can be a regular contamination, or they can be because some at high temperatures some nanoparticles might be generated as well, or at high temperatures some nanowires can be broken. So even though we are not 100% sure about what is the reason for that, so that's different. That's clearly because of at higher temperature. So that can be either broken nanowires or like new nanoparticles generated in the ink as well.
Okay, thank you.
Thanks for all the audience questions. Is there any other questions? If no, yeah, we can end here. And just to remind that we have a evaluation form. The link is given in the email. So if you're interested in this presentation, you can fill out the evaluation document. So thanks for all the audience to attend this graduate seminar. Thank you.
Thank you.